So it's important to know which units stand for which quantities. So I think that maybe we're familiar with some of these things. Hopefully that you know a meter is a measurement of length. So something can be a certain number of meters long. A meter is not a measurement of mass or anything like that. And the mass would be measured in kilograms or grams. If we're working in lab, a lot of times we have smaller amounts, so we might have grams. If you're working with biochemistry or medicine, you might have milligrams or micrograms of something, but a gram would be a type of unit of mass. So these quantities are all very different from each other. You can't have the same unit for time that you do for temperature because they're very different from each other. The same thing with mass and length. Mass is just very different property than length is. They can be related. You can have a certain type of rope where you know that so many meters of that rope have a certain mass, and you can express that relationship between the length and the mass, but the mass measurement is very different from the length measurement. It has a different unit. We're not going to be working with current or luminosity very much in this course, but they are also different quantities that have their own SI units. So for completeness, I included them here. There might be other properties that a substance has that can be measured. It can have a volume. It can have, in chapter 3, we're going to go into specific heat, so that property of material, but that would be expressed in different units, and those different units can be converted into SI units if need be. So for example, volume, there's not a specific SI unit of volume, but volume is a three-dimensional space, so it's length cubed. Length times width times height, but 3 length measurements cubed. And so the SI unit for volume would be cubic meters, because each length measurement has a unit of meters. So meters times meters times meters would be cubic meters. So that is one way to express volume using SI units. Speed is a relationship between distance traveled and the time it took to travel that distance. Distance is another word for length. Distance would be measured in length, possibly meters. And then time measurements can be measured in seconds or hours or minutes. But we have these two quantities together make up the speed. And so if we wanted to use SI units to measure these two quantities, length over time, the official SI unit for length would be in meters. The official SI unit for time would be in seconds. And so meters per seconds would express speed in SI units. A lot of times when we are not talking about SI units, you might express speed as miles per hour. So that's another unit for speed. If you are into boating, you can express speed in knots. That's all I can think of right now, but there could be other units for speed. For volume, another common unit that we use for volume as opposed to meters cubed is liters. 1,000 liters is a cubic meter. That's quite large. A cubic meter is quite large. Even a liter is quite large. A lot of times we express volume in milliliters in lab because that's more manageable. Those are the kinds of volumes that you have in beakers that are a convenient size. It's good to know that 1 milliliter is the same as a cubic centimeter. So if you had a cube that measured 1 centimeters on each edge, and you filled that with water, you would have 1 milliliter of water inside. If you filled 1,000 of these with water, you would have 1 liter of water. Some other possible units to measure volume that are not SI units, I can think of a couple. Here in this country, we use gallons a lot. If you're cooking, you might use cups. You might use teaspoons. So these are all ways to measure the volume of something. The LibreText points out that weight and mass are actually a little bit different. Mass is something inherent in a substance. So a particular particle would have a mass no matter where it's located. That particle could be weightless in outer space because the weight is dependent on the gravitational force that that piece of mass is experiencing. However, we will be using this relationship between a mass of 1 kilogram and a weight of 2.20 pounds. That is what a mass of 1 kilogram experiences on Earth. So we'll go ahead and use this mass to equal this weight, even though technically they are slightly different properties. So again, I mentioned that 1 kilogram would not be equal to 2.20 pounds if we were in outer space or on the moon, which has lower gravity, or on a different planet like Jupiter, which has higher gravity. But we are not going to worry about that too much in this course. So the SI unit for mass is a kilogram. For weight, the SI unit would be slightly different. So the weight is a unit of force, which is mass times acceleration. And acceleration is length over time squared. So the unit for force would be mass times length over time squared. And now we have properties that we know the SI units of. We have kilograms for mass, meters for length, and seconds for time. The SI unit for temperature is kelvins. That's in the table up above. But heat is not the same. The unit for heat would be the same as the unit for energy. And the SI unit for energy would be kilograms times meters squared over seconds squared. The textbook mentions some other units for energy that we're going to be using in Chapter 3. One of them is a joule, and one of them is a calorie. We also have nutritional calories, which is with a capital C. Kilowatt hours is another unit for energy that you might see on your power bill. So we have different units for each of these properties.